Hey there, it's Jason Gorman from Codemanship with a video about modular design principles in C#. In a previous video, I looked at the principles of simple design. If you recall, this was a set of sort of a hierarchy of design needs for our software designs that we apply as our software is growing over and over again. We make sure the software works, we make sure it's easy to understand, we remove any duplication, remembering, of course, the rule of 3. And also, if we make it harder to understand, we leave the duplication in. And then from whence it gets its name, we do the simplest thing we could possibly have done, the simplest code, the simplest solution that will pass the tests. Now, in a minute, I'm going to be showing you some code that I think ticks all of those boxes, but still potentially has some design problems. And in this video, we're going to be talking about principles of modular design with the specific goal of producing software that allows us to make changes to the way that it does one piece of work without having to rewrite the rest of the code. So what we're trying to achieve here is what's called separation of concerns, a proper clean separation of concerns, so that we can make changes to the way that the software does one piece of work without having to rewrite big chunks of the rest of it. And that's all about how we manage the dependencies in our software, and how we then package up our code into small reusable elements that we call modules, so that as much as possible change is localized to individual modules. The first principle of modular design we need to think about is how much each module is doing, and the rule here is that modules should only do one job. Imagine you've got a class, for example, that does a business calculation, and it also saves the result of that calculation to a SQL Server database. Now, that's a module that has two reasons to change. I can imagine wanting to change from, say, a SQL Server database to some kind of NoSQL data store, or even a text file or something like that, without wanting to risk breaking the business logic. I wouldn't want that business logic to be affected. So really, I'd want those two pieces of work to be in separate modules so that I only have to change one of them. I can make a change in one place, and vice versa. I might want to change how the calculation is done, but not change how the result of that calculation is saved. So we split those apart so that each module only has one reason to change. The other advantage of building software or composing software out of modules that only do one job is that we get far more choices about how our systems can be put together out of individual modules. So we get far greater, what I call, composability of software, but each module is only doing one specific job. To use an example from the physical world, think about hi-fis. So you've got your integrated hi-fis that put everything all in the same box, essentially, your CD player and your radio and your amplifier and so on. And then you've got your modular hi-fis, where each module in the hi-fi system only does one of those jobs. So there's a CD player, and there's a separate amplifier, and there's a separate set of speakers, and etc. Now, with the integrated hi-fi, you get one choice at system configuration, basically. You get the JVC turntable with the JVC CD player, with the JVC radio, with the JVC amplifier, and the JVC speakers. But with a modular hi-fi, you can have the JVC turntable, but you can use your Sony CD player with your Denon amplifier. Maybe you don't even want a radio, maybe you don't listen to the radio, and maybe use your JBL speakers. So you get far more choices over how the system can be composed out of those individual modules, because each of them only does one job. So for that reason, we say that modules should only do one job or have one reason to change. It's also important that modules know as little about each other as possible. So we're talking here about something called coupling. A coupling is when a module references some feature of an external module, some other module. For example, when a class references a field or a property of another class, that creates a coupling. And couplings are the things along which change propagates. So if I'm using your method and I then change the signature of that method, I have to rewrite my client code as well. So that's what these ripples that spread out when we make changes, they spread along those couplings, and we're trying to reduce those couplings as much as possible. And the way that we do that is we encapsulate as much as possible the internal workings of how that job is done. How does that module do its job? For example, what data does it use? Well, the client shouldn't need to know that. The less the client knows, the better. The less couplings the client has to its suppliers, to the other modules it's using, the less chances are that we'll need to change that client module when we change the internal workings of those suppliers. Now, the style of design here is sometimes referred to as tell, don't ask, and we're going to see some examples of this. But essentially, in enterprise computing, it's become a kind of very much the norm that we have objects that do work for, they do business calculations, for example, and objects that store data. You might call them data classes or entities or business objects. So there's objects that have logic and objects that just have fields and relationships that represent the data that logic is acting on. In order for the classes that have the logic to do the work that they need to ask for the data from those data classes. And that creates large amounts of low-level coupling, all those getters that we're using to get at that data. So we're asking for the data and then doing the work, and then we're exposed to those internal details. And whenever they change, we might have to change as well. Our code gets broken. If we were to flip that around and put the work where the knowledge is, so if we put the work where the data is essentially, so that we encapsulate that as much as possible in the same module, then we're able to limit the amount of information, limit the coupling that is required in order for one module to use the other module. So we tell, don't ask. So we tell the object that has the data to do the work, rather than asking for the data to do the work ourselves. The third thing we need to think about is how those dependencies are set up. So we've got one module that uses another module to do a particular job. There's two ways we can set up that relationship. One way is that the module that uses the other module could create an instance of that object, which means that it knows what kind of class it is. It knows what its implementation is. And that means that it's not possible then to replace that implementation with a different implementation without rewriting the client code. So instead, what we try to do is we try to make that dependency swappable, usually by dependency injection, by passing the supplier object in to the client in a constructor, for example, or as a method parameter. So it's passed in from the outside, and that means that it is possible, with a bit of design thinking, to substitute a different implementation of that supplier without rewriting the client. So again, it's another way of achieving the ability to change one module without having to rewrite all of its client modules. So we need to make sure that our dependencies are swappable, usually by dependency injection. And then finally, and this is kind of language specific, we need to think about what modules are exposing to their clients. Now, in JavaScript or Ruby or Python, this is not really a problem because we have dynamic typing, or what's called deduct typing. So it's only binding to the features that it's actually using at runtime. So you might have a class with 10 methods on it, and maybe the client is only using 2 of those methods, but that's not a problem because it's only binding to those 2 methods. It doesn't know about the rest of the methods. C# does not work that way. Languages like C# and C++ have what's called binary compatibility of interfaces, such that if you're using a class that has 10 methods on it, but you're only using 2 of them, and any of the other 8 methods are changed, you then need to be recompiled, retested, and redeployed because you're binding to that whole type. We call that binary compatibility. So with those kind of statically typed languages, it's something we do need to think about, what's being exposed. So the principle here is that we only expose interfaces that are client-specific. They only include the features that the client is actually using. So in the case of our class that has 10 methods, but our client is only using 2 of them, we would extract an interface specifically for that client to use that only exposes those 2 methods. So that it's only affected by changes specifically to those methods and not to stuff that it's not using. So it's another way of hiding stuff, if you like, from the client. So those 4 things taken together in C# can be applied at the class level. They can also be applied, as we'll discuss a little later, at the assembly level and at the level of assemblies of assemblies, systems and subsystems and microservices and that kind of stuff. So it's all about how we package things together as much as possible to make it possible to change how one piece of work is done without having to rewrite the rest of the system. So it's all for that, what we call separation of concerns. Separation of concerns is what we're trying to achieve here. Now, all very well talking about this, let's look at a simple example. So I've got some code here that is very straightforward, and let's just check if it ticks all the boxes of simple design. First of all, does it work? Well, let's run the tests. Looking good, it's working. Let's read the code here. It's a carpet quote, fitted price, room length, room width. We're multiplying those together to get the area. We're seeing whether or not we need to round up to the nearest square meter there. And then we're multiplying that area by the price per square meter of the carpet. So that kind of, to me, that clearly communicates what's going on here. So I'm going to tick that box as well. This code clearly communicates its intent. What about duplication? Well, I can't really see any in this module. Let's take a look inside our test. So there's a little bit of duplication going here. We've got two tests that are very similar. But I think actually I'm going to live with that. I think it's actually easier because these are two different rules. One is for when we're not rounding up and one is for when we are rounding up. I could parameterize this and make a single test method and have a parameterized test. But I think that test method then would be overloaded. It would be testing two different rules. So I'm not a big fan of that. And also it's only two examples. So if you go back and look at my video on duplication and the rule of three, usually on average, I wait for 3 examples of duplication before I refactor it. And I think I would be quite prepared to live with this, to be honest. So we're going to tick that box as well. There's no duplication that we really need to worry about. And then finally, is this really the simplest way that I could have calculated this fitted price? I think it is. I'm struggling to see a simpler way, so I'm going to tick that box as well. So it's ticking all 4 boxes of simple design, which means that it's good code. It's not to be sniffed at. Having said that, it's not without its problems. Now, we have a conversation with the customer for this particular mini system, and the customer tells us, well, the rooms don't always have a length and a width. Sometimes they're L-shaped. Sometimes they're circular rooms, and then we would calculate the area of the carpet required differently. So we can imagine now that we would want to change how this works without changing how this works. We'd like to be able to change this without touching any of this or risking breaking any of this. The problem at the moment is it's all in the same module. I would also like to be able to vary these two things independently. Vary how we calculate the area of a room, vary how we calculate the price of a carpet independently of each other. And at the moment, the only way we can do that is to keep rewriting carpet quote. And we don't necessarily want to do that. So what we're going to do is a little refactoring here. We're going to modularize this. So we're going to end up with each module only doing one job, each module telling, not asking, so they encapsulate their internal workings. Modules are going to have swappable dependencies. So carpet quote is essentially going to get references to the modules that it uses by dependency injection. And then we're also going to double check whether our interfaces, our carpet quote here has been exposed to any features that it's not actually using on the interfaces of its suppliers. So we're going to see if we can tick all the boxes of modular design with this simple code here. Now, a good place to start when it comes to object-oriented programming is to think about objects. And the problem at the moment is that we don't have any. We've just got carpet quotes. And I can spy, for example here, I think that's an object that has a length and a width. So maybe the first step, and I will often do this, is to start introducing objects, data objects essentially, to represent what data we're working with. And then we'll look at those data objects and we're going to look for something called feature envy. This is a code smell that's described in Martin Fowler's excellent book. Feature envy is when a method of one class has envy for features of another class that it's using, giving a strong indication that that method is in the wrong class, that those internal workings have been unencapsulated, they should be hidden. And we'll do that by moving that method to where it really belongs. So let's start by introducing some data classes here. Now I'm going to use a refactoring called transform parameters. This is available in Rider. I believe it might be called the same thing in ReSharper. I haven't used ReSharper for a while. So if you're a a resharper user. It might be called transform parameters. It might be called introduce parameter object. I can't remember. But what I'm interested in is these two parameters here. I believe these are parameters of, these are fields of a room. So what it's going to do is it's going to introduce a room parameter and pass it in with that data represented as fields. There we go. And of course, immediately rerun the tests. Now let's take a quick look at this room class. So it's got a room length and a room width. Room.roomLength sounds a bit wordy now, so let's rename those. Let's fix that. Sorry. In actual fact, maybe I will rename these properties. That'll probably be the simplest way of doing it. So that's just length, and we'll rename the parameters to go with it. Jolly clever. These automated refactoring tools from JetBrains. There we go. So now it's just room.length, room.width. That's a nice little cleanup we've done there. And this probably now belongs in its own file. So let's move that to its own file. Okay, and immediately rerun the tests. Okay, now that we've got this data object, we've got a little bit of, I call this partial feature envy. So fitted price, this method has partial feature envy for room. That is to say that it has an unhealthy fascination with the internal data of room and with those length and width properties. Now, to fix this, what I'm going to do is I'm first of all going to extract a method to get this expression on its own. Let's just call that area. So it's the area of the room. It doesn't need to be static. Okay, and you can see now that this area method here, it's not about the carpet quote, it's all about the room. It's all about the room. That's what we mean by feature envy, basically. This method is all about the room. So what I'm going to do is I'm going to move this to where it arguably really belongs. Okay, it's going to bump it up in terms of visibility so that we don't break the code there. This is why I like these automated refactoring tools, because 9 times out of 10 they don't break your code. Now when we take a look inside a room, okay, so now what's happening here is that rather than asking for room's length and width and doing the calculation itself, it's telling room to do that calculation. Tell, don't ask. And what that means is these properties do not need to be exposed. We can make them private. So we are now hiding the internal workings, hiding the internal details of how we're actually calculating the area of the room. So that's essentially what we mean by encapsulation. Internal details are hidden. So all it knows is that it can tell a room to give it an area. That's all it needs to know. Now we can rinse and repeat. This code here is all about calculating the price. And again, I think there's an object lurking in here with these two parameters. So let's use that same transform parameters refactoring. And we're going to create a data object that has those two as fields. And it's a price per square meter of a carpet. Okay. So carpet becomes the parameter. And now, similar kind of thing here. We've got a little bit of partial feature envy. Part of this method is all about the carpet. So let's get that on its own. In its own method, let's call this price. I think it's probably made it static. We didn't need to do that. This fascination with static methods, I do not understand it. Okay. And it's a similar kind of deal here. This has feature envy for carpet. It belongs on carpet. So let's move that. Bumps it up so that we can see it from here, so that we don't break our code. And we can clean up a bit here. We can inline that. Okay, there we go. So now carpet code is greatly simplified. It tells the carpet to calculate a price. It tells room to calculate an area. It doesn't know how the area is calculated. It does not know what data is involved. does not know how a price is calculated, it does not know what data is involved. So it can only be affected by changes to these methods, the public sort of facing aspects of these methods. So it knows a lot less. Its job now essentially is just to coordinate. That's all it does. It coordinates the work here. Now, again, I think carpet probably belongs in its own file. So let's move that first. And again, these do not need to be public. We can encapsulate here. There we go. And rerun our tests. So price is doing its work with its data. Carpet is doing its work with its data. Room is doing its work with its data. Carpet quote just tells them to do the work. It's just coordinating. Each of our modules is only doing one job essentially. One coordinates, one calculates the price, one calculates the area. They are hiding how they're doing that. So carpet quote only knows that it can tell carpet to give it a price. It can tell room to give it an area. So tell, don't ask. So we got rid of that feature envy, and now that's all encapsulated. So we're ticking 2 boxes of modular design already, but we're on the way, well on the way to ticking the 3rd box, and that's because our room and our carpet are being passed in. Now, this is very language specific. It wouldn't actually be in C# that easy to extend room with a different implementation. For example, let's say a circular room, because we would need to change the design of this class, for example, to make area virtual so that we can easily override it in a subclass. Now, I'm not a big fan of implementation inheritance generally, so I think a cleaner way of redesigning this and refactoring this to make it much easier to swap with a different implementation would be to extract an interface for room. What I'm going to do here is I'm going to, first of all, let's be clear about this. This is a rectangular room. So this is a specific implementation of room. I'm not going to rename any of the other references to it. Okay. No, I want to keep that as room. Thank you. Okay. Now the reason I've done that is because in a minute I'm going to extract an interface. And this interface is only going to expose what carpet quote needs to see, which is that. That's all it needs to see. So we can extract a client-specific interface. So we're going to kill 2 birds with 1 stone here. Let's extract an interface for a room. And we're going to call that just iRoom. Sounds like the kind of thing you might find in a hotel that's run by Apple. There you go, an iRoom. Put it in its own file. Yes, please. And you'll notice that its properties are not exposed. We're only exposing what the client needs to see, which is just the area method. That's the only thing it needs to see. Okay, let's rerun our tests. And now if we go into carpet quote, we can actually change this dependency. It'd be nice if it did it itself. We can change this dependency so that now carpet quote only knows about the interface. And at that point, we have sort of pure dependency injection in C#. It only knows about the interface. Okay. Now that we've done this, it becomes possible to extend, or rather in this case to replace, to substitute a different implementation. Let's create another one here. Let's call it a circular room. And if we make that implement our iRoom interface, like that. And now if we give it, so its dimensions are going to be different. So if we say that a circular room, instead of a length and a width, has a radius, and what we're going to do to calculate the area, we're just going to square the radius. So if the radius, for example, is 10 meters, the area of the carpet required that the customer would have to buy would be 100 square meters. And now that we've got that little implementation there, we could substitute here, for example. So instead of a rectangular room, we could make that a circular room. Oops. And let's say that it's 10 square meters, so we give it a radius of 10. And now we would expect the final price to be 10 times 100 square meters, so 1,000. Now, as I'm doing this, you will notice that I have not, in substituting here, I do not have to rewrite this. And this is the whole idea here. Carpet quote and how it works does not need to change. It does not need to know that it's a circular room. That is somebody else's problem. And that's what we mean by true separation of concerns. Make it somebody else's problem. Now, when I run this, hopefully, this will pass without making any changes to carpet quote. And there you go. And that is the essence of good modular design. Each module is only doing one job. As much as possible, they're hiding their internal working, so the clients don't need to know how that job is done, which makes it much easier then to change how that job is done, either by editing the client or by substituting a different implementation by dependency injection. And then finally, we take a look at our iRoom interface. It's just exposing what carpet quote needs to see. None of the other features of a room, whether it be rectangular or circular, are exposed. So that interface is client specific. Now, that's at the class level. How does this scale up? So we're going to talk very briefly now about how this applies to assemblers, for example. So assemblers can also be thought of as modular. And they have many of the same properties. For example, we can swap an assembly with a different assembly that has the same, implements the same interfaces. And that indeed is how many frameworks work on the .NET platform. Well, the same principles apply, but just at a higher level of organization. So for example, in our project here, we have a bunch of classes that are collaborating to do one job, which is to calculate the price of a fitted carpet. So that will be what this assembly does. And it will contain the classes that are required to do that job, and only the classes that are required to do that job. We would want as much as possible for the inner workings of that assembly to be hidden from other assemblers. So it might be, for example, that in our final design, the only public class would be carpet quote. And the only public method would be fitted price. And the rest of these classes would be hidden. They would essentially be internal to this particular assembly. Those details will be hidden so that assemblies are coupled, or rather classes inside different assemblies are coupled to each other as little as possible. So those assemblies hide their internal workings. But now we're not talking about sort of fields and methods, we're talking about classes and interfaces. It hides those. And we can also make assemblies easier to swap. So this is about how we design at that kind of level. So it may be, for example, let's think of ActiveX data objects, ADO, that old thing. And before that, ODBC and those kinds of libraries. So you would define a DLL that contains a set of abstractions, a set of interfaces for a kind of database. For example, a SQL Server ODBC driver, or ADO driver, or an Oracle ODBC driver. So you would define the interfaces that all ODBC drivers need to implement, and you would put those in one assembly or in one DLL, if we're going backwards in time to the days of COM. And then you would have implementations of those interfaces in a separate assembly. So all the concrete stuff, all the classes that know that it's an Oracle database and so on and so forth, would then implement those interfaces, and your clients would only bind to the abstractions. They would only bind to the abstractions. So all your dependencies would be on assemblies that contain abstractions and not necessarily lots of concrete classes, lots of implementations. And that then it makes it possible, as we've seen, for example, with ADO and ODBC, to swap different database drivers without having to rewrite your client code. That's the whole idea there. So that's the same principle applied at the assembly level. So all those concepts, assemblies doing one job, encapsulating as much as possible, hiding their inner classes, if you like, and exposing as few classes or interfaces as they can to their clients, and also making them swappable by creating assemblies that are all about abstractions, and then having separate assemblers that implement those abstractions, for example, those interfaces. So your client only needs to know about the assembly with the abstractions, and it only needs to bind to the abstractions. So then we can swap in different assembly implementations at runtime even without having to change the client code. And again, we can scale this up. So we might have web services or microservices, for example, that are made of multiple assemblers. So we would package those assemblers together into some unit of deployment, like a microservice, maybe deployed inside a Docker container altogether. And it's the same thing. Those assemblies will be put together because they're part of a larger job. For example, you might have a web service or a web system that is all about calculating invoices for carpets, that involves calculating quotes and other related tasks. And only the assemblers that are involved in that would then be deployed along with the database that's required and etc. itself, encapsulated inside its own container. And each container would have one higher level responsibility. They would know as little as possible about any other services or any other containers or processes that they communicate, that they have to use. So they hide their internal workings, which means a lot of their assemblers will essentially be internal to them and may be exposed just through a web service. And again, those dependencies, in the case of the web, you would make them swappable because you're using the web, and therefore you've got some swappability. You just need to point the client. You can even swap in, you can even do it dynamically with a bit of network jiggery pokery, so that essentially you just redirect them to a different server, but they're always going to the same URL. So there are other ways of achieving swappability that are quite straightforward to do on the web or on TCP/IP on the internet. So at every level of code organization, essentially the same principles apply, just at a larger level. So the way that we package code into methods and what those methods know about each other, the way that we package methods into classes along with fields and what those classes know about each other, the way that we package classes into assemblies and what those assemblies know about each other, the way that we package assemblies into, for example, web services or containers or however we're subsysteming it, and what those subsystems know about each other, and so on and so forth. At every level of organization, the same principles apply, and they're all about being able to change one thing without having to rewrite the rest of it. Now, I'm going to leave you with one final thought. It would be really, really, really nice if more developers and more teams and more organizations who create software that other people write software around, for example, APIs, web services, applied these principles a bit more rigorously, because I've worked with a lot of teams and I watch a lot of companies fight on a daily basis with changes to public interfaces, changes to APIs that are not backwards compatible. In other words, not swappable. Either they're not binary compatible, in other words, we've actually changed the signature of a method and now everything's broken and need to be rewritten, or changing the rules, changing the contract between, for example, two, a client, a web client and a web service, such that now the client is broken. So it's binary compatible. We haven't changed the signature of the function or the web service, but now that we've changed the rules, maybe we've added a precondition that wasn't there before, and now all the clients are calling it and it's not working. So you really, really, really do need to think about this stuff. You need to be very, very mindful of this stuff. And it starts at the class level. It starts at that level of organization, because the dependencies between assemblers are actually dependencies between classes in different assemblers. So they're class dependencies that cross the boundaries between assemblers. And likewise with assemblers at the subsystem level, it's dependencies between assemblers, which are dependencies between classes inside those assemblers. So they're all ultimately dependencies between classes. A class in one subsystem or system needs something done by a class in another subsystem, and therefore they need to have a dependency. So you need to pay attention to the dependencies between classes, and especially pay attention when those dependencies are passing over those boundaries between, for example, two classes in different assemblers. So I would, particularly when it comes to dependency injection and using interfaces, you might be absolutely fine with saying, well, we're not going to go mad with the interfaces and have them everywhere willy-nilly, because that can get very cluttered. But maybe say, well, we'll definitely do it for dependencies that cross the boundaries between assemblers. because that's where those dependencies can really hurt you. Because as we scale up those dependencies from classes to assemblies, and from assemblies to services, and from services to systems, and so on, the organizational cost of those dependencies multiplies. It goes up exponentially. So it may be that the dependencies between two classes are two classes that you have written in your code, in your project, and it's not really a huge problem. But between two assemblers, those could be assemblers that are being worked on by separate developers, or even by separate teams. And then if I need a change made, or if I'm making changes to code that's breaking other people's code, the impact is now spreading out through, not just through a single code base like my project here, it's spreading out through an organization. The ripples are now spreading beyond just the code that you're working on to code that everyone else is working on. And the cost of those ripples starts to multiply. It really does hurt you. So if you've got dependency problems at the class level, and then you think, but if we break this up into microservices, that will solve the problem. No. You've now got the same dependency problems, but now you've created a big organizational problem as well. This is now a problem for multiple teams. So if you can't write a nice modular monolith, a single assembly that's nice and modular inside, don't even think about web services or microservices. Don't even go there. Sort out your dependency problems and then start breaking it up. Because otherwise all you're doing is you're just amplifying those dependency problems manyfold and creating big headaches for lots of teams. Okay, so those are modular design principles. Coupled with the principles of simple design, the idea is that as our software grows, one test case at a time, we stop and we do a little code review. So we look at we code and go, is this simple design? Does it work? Is it easy to read? Is there duplication? Remember the rule of 3. And is it the simplest thing we could have done? And also go through and look at, is this module only doing one job? Is it asking or telling? Is there encapsulation there? Can I see feature envy? That's the thing to look out for, feature envy. Can I see feature envy? Does stuff need to be moved around? Do these dependencies need to be swappable by dependency injection? Remember that that's especially important when that's a dependency that's crossing the boundaries between, for example, between assemblies. But I would say, generally speaking, it's a good idea to compose it that way. But maybe don't go mad with the interfaces. Maybe don't have interfaces everywhere. So maybe just do the interface thing when it's crossing those boundaries, or when it's a key dependency, something that you're very keen to hide. And in languages like C#, you do need to be thinking about what clients are exposed to that they're not using, and consider whether or not those interfaces need to be made client-specific. That's something for C# developers to worry about. And don't forget that these principles apply at multiple levels of code organization. So you start, if you're TDDing a system, you start with one method on one class, and that soon becomes multiple methods, and then you realize that class is doing more than one job. So you split that class up, and then those 2 classes become 4 classes, and those 4 classes become 8 classes. A bit like cell mitosis, the way that cells divide and grow and divide and grow and divide and grow. And then eventually you're going to have a bunch of classes that are about one specific responsibility, like calculating quotes for fitted carpets. And then you think, okay, maybe I've got other classes in this assembly that don't really belong here. They belong in their own assembly because they're about another job. So you would then, your one assembly would become 2 assemblies, would become 4 assemblies, that would become 1 microservice, that becomes 2 microservices, that becomes 4 microservices. And it kind of grows organically like that, with you applying these rules over and over again, and allowing a modular design to emerge that has that nice clean separation of concerns, which we're really going for. Okay, I lied. There's one more thing that we need to touch on here. And this is the relationship between unit testing and test-driven development and modularity. So in unit testing, what we're saying is that our tests do not involve external dependencies. So they don't involve reading from databases or using web services or anything like that. And the way that we achieve that is using things called test doubles, like stubs and mocks. And the way that we're able to write tests with stubbed implementations, for example, that return hard-coded test data, or mocks that record when messages are sent to external dependencies, is through dependency injection. These things need to be passed in from the outside, and that makes our code inherently unit testable. So there's a very close relationship between modularity, between separation of concerns, and the unit testability of our code. You can't achieve one without the other. Now, test-driven development starts from the perspective of we're going to write the tests first and then write our code to pass the test. Now, if we're doing TDD well, if we're doing it right, that means that our code is going to be inherently unit testable because that's how we wrote that test, which means that it's going to end up more modular. So test-driven code has a tendency to end up being, if it's done well, has a tendency to end up being more modular as a side effect of doing it in a test-driven way, of writing those tests first, and then that drives us to a design that makes those other dependencies, particularly those external dependencies, more easily swappable. So these things very much work hand in hand, and the relationship between unit testing and test-driven development and modularity is the pathway to that testing pyramid that we're going to be talking about in a later video. In order to get fast feedback loops, we need to be able to build our software and deploy it quickly in minutes rather than hours or days or weeks. As our code grows, the lion's share of the time that it takes to build and release the software will be taken up by how long it takes to test that it still works, that it's fit for release. If your tests run really slow, if you've got a suite of browser-based tests, for example, then they might take hours, or even I've seen tests that take days to run. So your build cycles are going to be very slow, and that's going to become a severe bottleneck to the whole delivery process. That's essentially going to stop you from being agile. You're not going to be able to do those rapid releases, those rapid iterations, and get that end user feedback as often as you need to. And also it means that for large periods of time your code is going to be broken. If it takes 3 days to retest it, that means that's 3 days of coding where you're merely breaking stuff and not knowing it, and the cost of going back and fixing that is going to be orders of magnitude higher than if you'd discovered it straight away. So for all those reasons, we need test suites that run fast, and the key to test suites that run fast is modularity. Those design principles. So particularly these principles of modular design, but also lack of duplication as well. We'll talk about this when we talk about the testing pyramid, are what help us achieve test suites that are mostly made up of fast running unit tests. The vast majority of our tests run fast. So modularity is very, very, very important. Very important. The gateway to modularity, as we've seen, is refactoring. So you can plan all of this stuff and think, well, I think we'll need this module, I think we'll need this interface, but we tend to find that the best designs happen as a result of writing code that works, write the simplest code that works, and then review the code and look at it and go, but is it modular, or do we need to refactor it? And we can introduce those abstractions, we can introduce new classes, we can introduce parameters, we can introduce interfaces, and so on and so forth, through the process of solving these problems of modularity, and introduce separation of concerns, not because we just think we should have it, but because we actually needed it to solve that particular problem in that particular design. So basically optimize the code that's in front of you. Look at the code that you've written that does the work that you need, the code that works, and modularize that, refactor that. Okay, so there's lots to think about there. And couple this with the video, if you've not watched it already, on Simple Design. I'll post a link in the description below, as well as a link to this source code so you can have a go at these refactorings yourself. In the next video, I'm going to be talking about specification by example, and this is going to be very much where the rubber meets the road, which is the big question of all, which is where do these tests come from in the first place when we're doing TDD. So we're going to be looking at how we can drive a whole development process working directly with our customers and with other people on the team, not just necessarily developers. So subscribe and ring the bell for notifications if you're interested in the videos that are coming up. Hope this has been of some use, much food for thought, I think. Now go take a look at your code. Is your code modular?